Hello Pre-Calculus, I've got a video for you guys to kind of start off trig, all right, the study of right triangles. So, we're rolling, the semester is pretty much wrapping up in the next week, but I figured we could take a few days to just lay out, all right, what are some of the basics of right triangles, and can we get a very, very, very superficial sense of of the six trig functions. But today, 5.1 is all about, can you work with right triangles? So, if somebody asked you to find the missing side of these two right triangles, the thing that we're hoping that you come up with is the Pythagorean theorem right off the bat. The Pythagorean theorem relates the three sides of a right triangle. If you want to go down a YouTube rabbit hole, you can research Pythagorean theorem and Pythagoras. He's a Greek mathematician from way back in the day. Some weird stuff went on with those people. So if you're curious, proceed with caution. But anyway, the Pythagorean theorem states if you've got two legs of a right triangle, we'll just call them leg A and leg B, and the diagonal, also known as the hypotenuse, is the value c, then every single time a squared plus b squared will always equal c squared. And there's a bunch of different proofs related to this. Our former president, James Garfield, he published a proof of the Pythagorean theorem. And in past years, I've done this, but it seems to make a little more sense to do so in person. So I'm just going to let that be for now and see if we can apply the Pythagorean theorem to solve for both x and y. So in this context, the a would be, 1. The b would be x. The c, hypotenuse, would be 9. So a squared plus b squared equals c squared. Legs on the left, hypotenuse diagonal on the right. So to solve for x, we're going to actually square 1, square 9, that's 81. We got to get x by itself, so you're going to subtract 1 from both sides. X squared is equal to 80. And then you got to square root both sides. Now remember, we had situations where square rooting both sides created both a plus or a minus, but since we're talking about just a length of a triangle, we're not going to be determining length in terms of negative values. So we can ditch the negative and just say x equals root 80. Now I also want to dig up the skill of being able to simplify a radical. Okay, so there's a couple different ways in which we can simplify radicals. That sounds like a government project, simplifying radicals. So then 80. Here's what you can do. First strategy is to use total prime factorization. So that's the factor tree where you say, hey, 80 is 2 times 40. Hey, 40 is 2 times 20. Hey, 20 is 2 times 10. Hey, 10 is 2 times 5. And then what you do is you say the square root is any number times itself becomes that whole number outside of the square root. So the square root of 2 times 2 is equal to 2. The square root of 2 times 2 is equal to 2. So this is really 2 times 2, which is 4, and then you've got a root 5 left over. So this is equal to 4 root 5. And maybe this isn't the best visual of how you'd do it. A lot of people would say, rewrite root 80 as 2 times 2 times 2 times 2 times 5. And people are like, hey, this is like the square root of 4. 2. Square root of 4. 2. 2 times 2 is 4. There's a 5 left over. Yeah. Also recognize that this can be written as a decimal approximation. So get used to both the simplified radical version of things as well as a decimal approximation to the nearest, let's go thousandth. That's 3 spots past the decimal. So 4 root 5 as a decimal is going to be 8.944. Okay. First example, taken care of. Second example, again, apply the Pythagorean theorem. In this case, you have both the legs, a squared plus b squared equals c squared. So then you can actually just add together 81 and 49, which ends up being 120 plus 10, 130. And then you're square rooting both sides there. Yeah. Oh, by the way, I forgot to show you the other way of simplifying 80 as a square root. If you find that 80 is the biggest perfect square that divides 80, you can split it up like that. And then just say root 16 is 4 root 5. But anyway, sorry about that. Kind of jumping back and forth between previous examples. Anyway, example 2, all the way. Root 130, it doesn't end up actually breaking down any further. Sure, 130 is even, so I can cut it in half. Half of 130 is 65. But beyond 65 is kind of a funky number. I mean, you get 5 times 13, and these are both prime, and there's no doubles of the prime numbers to take out of the root. So it's like, you can't simplify it anymore. Root 130 is the simplified version of that radical number. And the square root of 130 as a decimal, it's going to be 11 point something. 11.402. Okay, so I'm hoping you guys are like, hey, I've done this before, and I'm pretty confident with the Pythagorean theorem. We're just making sure we have this mathematical skill down. And when I mean this mathematical skill, I mean being able to produce this without a calculator that just straight up tells you. Okay? So beyond finding just a missing side, another task I'm going to ask you guys is to find the area of a triangle. You're going to see some applications of this later on that are a little more complex than what I'm talking about in 5.1. So let's say you're given a triangle like this, and I'm going to keep them as right triangles. So let's say, you know what? One second. Let's say finding area of right triangles. So our first one over here, I'm going to give you guys as, we'll say this side is 8. This side right here is 5, and we just don't know what this side is. Now the area of a triangle is given by the formula half base times height. And I think it makes a whole lot of sense when you talk about a right triangle in terms of half a rectangle. See what I'm talking about? The area of a rectangle is length times width. Okay? So the base of this triangle, if we look at it from the perspective that this is the base, matches with a height here. Length times width is the same as base times height. And here's the deal. If you're ever confused about like, well, what if the 8's the base? Well, you can make the 8 the base if you can actually find the height that connects you from here to there. It's going to be a whole lot easier to say, hey, let's just make this the base so that this one is automatically the height. The right angle is what tells you what connects the base to the height. All right? It's kind of like the base and the height of a triangle are perpendicular bisectors. I almost said bicycles. Bisectors. They form right angles when they connect. So, I need this side to be able to compute the area. So I first have to apply now the Pythagorean theorem to find that unknown side. So a squared, we don't know what it is. I'll just leave it as the variable a. b squared is 5 squared, c squared is 8 squared. So a squared plus 25 equals 64. Do a couple calculations. And you get 39. Yeah, and root 39 ends up just being 3 times 13. Doesn't simplify any further. Root 39 goes here. Then our formula says 1/2. Base is 5. Height is root 39. And you're going to get kind of a messy number out of that. It's going to be 5 root 39 over 2, which of course can be approximated by a decimal. Which gives you 15.612. And keep in mind that area always has square units to it. So if you're given something like, hey, this is 5 inches here, and this is 8 inches here, and that's 8 inches there, you are multiplying an inch dimension times an inch dimension, which creates an inch dimension, inch squared. Okay? It's also kind of like common knowledge that a two-dimensional computation, like you're trying to find an area of a 2D surface, it's a plane, you're going to have square units because it's going to be inch by inch. Okay. I don't think I need to show another example of this. I do have a couple of examples that I think are interesting enough for us to dig into. So I'm going to count on you guys just to kind of have these as references. I'm not gonna post this on Google Classroom. So if you want to write this out longhand, it'll be a good practice for you to do so. At any rate, on a Major League Baseball diamond, the pitcher's mound is 60 feet and 6 inches, with each base being 90 feet apart. So a baseball diamond literally looks like this. All right? So home plate is right here. First base is here. Second's here. And third's here. It's about as close as man has gotten to perfection as there is, 90 feet between bases. Somebody said that back in the day. Not my quote. At any rate, we're saying that the pitcher's mound is right here. And we know that this right here is 60 feet. Now, 6 inches, you could just say is 0.5 feet, right? 6/12. 6 inches over 12 inches. So I could just say that 60.5. And then we've got maybe this unknown distance here, but we know that the base path is 90 feet here. The base path is 90 feet, 90 feet, 90 feet. Now, considering these dimensions, find the distance from the mound to first base. So they're basically asking us to say, take this right triangle. So I'm just going to isolate this right triangle. I'm kind of like dilating it. I'm making it larger. If this is 90 and this is 60.5, what's the value here? The distance, I'll just call it D, from the pitcher's mound to first base. And this is not a big deal, right? We're just taking an applied problem here, visualizing something in real life, and applying the Pythagorean theorem to it. So the Pythagorean theorem says D squared plus 60.5 squared should equal 90 squared if we have a perfect right triangle. Yeah, and by the way, just for the purposes of simplicity for you guys, convenience, you don't have to actually multiply the 90 squared out. You could just say subtract the 60.5 squared from both sides. Okay? So it's 90 squared minus 60.5 squared, which, by the way, is not 29.5 squared. You can't just subtract the whole numbers here and slap a square on it. It doesn't work that way. And then you can square root both sides. So I guess what I'm saying is you can wait to plug anything into your calculator until this last move, which I'm going to do right now. So what is the distance from the pitcher's mound to first base? The square root of 90 squared minus 60.5 squared equals, I'm getting 66.631 feet. So the distance here from the pitcher's mound to first base is 66.631 feet. Hopefully these calculations are correct. I wrote this problem, I think, 6 years ago, so hopefully Mr. Owsley 6 years ago didn't make mistakes. All right, last one. Just more of a thought to ponder for you guys. So it's basically like a true-false question. Here, I'll give you guys a little close-up here so you can ponder it properly. Is this true or false? Any two right triangles with the same hypotenuse have the same area. I would encourage you guys to pause the video now. Just think about it for a few minutes and make a case for yourself. Do you think this is true or do you think it's false? Okay. So here's what I'm going to do first. In order to start the process of maybe even thinking our way through something like this, let's just provide anecdotal evidence. An anecdote would be a specific case where we're like, hey, can I think of two right triangles with the same hypotenuse that have different areas? Because if I can do that right off the bat, then I can show it's false. That would be the counterexample. So let's take a right triangle here. Let's say that the hypotenuse, and you know what? I'll get super technical here. Where's that yardstick? I will literally measure out the hypotenuse. So this hypotenuse is exactly 24 centimeters. So this specific right triangle has 24 centimeters for its hypotenuse. For its height, we've got 10 centimeters. And you know what? I can find the third side by just doing Pythagorean theorem. I'm not measuring the third side because I know it's not a perfect right triangle, but the Pythagorean theorem will achieve perfection for us. So a squared plus b squared, don't know what that is equal to c squared. So I'm going to skip a bunch of steps here. I'm going to say b equals the square root of 24 squared minus 10 squared. I subtracted that over and square rooted both sides. So I think this gives us, what, 476? Something like that? Root 476? Let me be 100% on this. 24 squared minus 10 squared. Yeah, we're good. Okay. Now, here's the reason why I even needed to find this, was because I want to compute the area of this particular case where the hypotenuse is 24 centimeters. So how would I find the area of triangle A? Well, let's call it triangle, because area is A. Triangle G. Why not? So the area of triangle G is equal to 1/2 times the base, or you know what? I can interchange the base and the height in multiplication because of commutative property. So I can do 1/2 times the height times the base if I want to, which means I'm just taking this decimal, which I'm going to use the exact decimal, times 5, because 1/2 of 10 is 5. All right, the area of this triangle is 109.87 square centimeters. Okay, let's pick a different triangle. So we've got 24 centimeters from here to there. Okay, so I just changed the angle at which the the triangle's moving upward. So now, this is 24, and let's see here. This is 17. So then 24 squared equals 17 squared plus b squared. I can find this unknown side by square rooting 24 squared minus 17 squared. So we're square rooting. We're getting closer to the answer. 16.94. Excuse me. Okay, area. 1/2 times that base times that height equals 143.999. So triangle H has an area of 143.999. Compare the two areas. Whoa, don't fall off now. 109 square centimeters, 144 square centimeters. Any two right triangles with the same hypotenuse have the same area? No! We just found two of them that don't. False. That's my counterexample, and that concludes the notes for 5.1. Thanks for sticking it out for the whole 22 minutes.